Everyone can hear me? Cool. Kia ora, I am Carlin. I work for sustainable engineering. This presentation was put together by myself and my colleague Alvin, who's based in the Philippines, so he's not with us today. Um, I am from Auckland. I grew up in West Auckland. I normally introduce myself as a part-time musician that likes being outside, but I also have a mechanical engineering degree, and that's come in handy. My background is predominantly in the building services space, but I took a slight shift into the passive house space a few months ago. So yeah, looked at PHPP for the first time about 4 months ago, and I've dived straight into it. And this presentation is about cooling loads. It's related to overheating, but it's not necessarily about how high temperatures get. It's about sizing cooling equipment. And just as an overview, I'm going to be talking about why cooling sizing is important, how PHPP produces cooling loads, how we can maybe adjust the settings in PHPP to get more accurate sizing occasionally if we need to. And then I'll be comparing it to dynamic thermal modeling approaches, which are more common in the sort of HVAC industry for sizing cooling equipment, and discussing what we found. Obviously, there's a lot that you should consider before you're sizing your cooling equipment. Bear that in mind. And this is a very narrow, technically focused presentation. Obviously, the passive stuff and the fabric stuff should always come first. And cooling system sizing, super important. Obviously, it's not getting any cooler. If you undersize it, people might end up uncomfortable, or the building might not meet their expectations. There's been some pushback on insulated housing in Aotearoa recently because it's getting too hot, and we don't want to be contributing to that pushback. But also, if we oversize our cooling equipment, it can lead to inefficient operation, and bigger equipment means more embodied carbon as well, which is also a consideration. So comparing PHPP to a dynamic cooling model, I've got the Energy Plus logo there because that's the software I used for the comparisons. It's not the only software you can use for a cooling sizing model, but dynamic models typically use hourly loads. It's on a zonal basis, so instead of one big zone like you have in PHPP, which represents a whole building, it's room by room. You have hourly inputs. These include the outdoor climate. They include indoor occupant activity and equipment loads. You might have certain cases where there's peaks in occupant or equipment loads. For example, if lots of people arrive at a certain time, you can consider those in a dynamic model. And PHPP, by comparison, gives you an average daily load. In the certification settings, this is based on an average daily temperature. It's a single zone model using standard occupancy rates and internal equipment loads. It also considers a soiling factor, which reduces the G value of the glass slightly, letting in slightly less solar gain. And actually, those certification settings are designed to size cooling for buildings that have low window to wall ratios, predominantly north and south sides that are well shaded, and where the thermal mass in the building can absorb the solar gain throughout the day, and you have background cooling on most of the time to deal with that. And that's not necessarily how we operate buildings in Aotearoa, and a lot of our buildings are a little bit more lightweight as well. So what have we done? We've modeled 2 standalone residential buildings and an apartment block in 3 climates. We've had 4 models for each case. So the PHPP with certification settings. We've adjusted some of the settings in PHPP to see if we can get maybe a more accurate cooling load based on this. I've compared it to a single zone dynamic model. The expectation is that the adjusted PHPP, which is a single zone model, will have similar characteristics to the single zone dynamic model, and then compared that to the results of a multi-zone dynamic model where all of the rooms are modeled. And yeah, Auckland, Wellington, Queenstown climates. Here's a rough overview of the buildings. I just looked at the top floor of this apartment block, and then a large family home and a slightly smaller family home. Both a 3-bedroom, but one had a considerably larger floor area, and standalone one, as you can see, also had slightly worse form factor. So this is about the settings that we adjust in PHPP to potentially get a more accurate cooling load model. This is based on work by Oliver Style from Praxis Resilient Buildings, a Spanish company. He's done lots of really good presentations about this, and we're building on the knowledge base that he's put together. So we're looking at what the weather conditions are that we're inputting into PHPP, what the occupancy rate is. Is the certification one okay, or do we expect more people for the cooling peak? The equipment internal heat gains, is the set point all right? Does your client expect 25 degrees to be the cooling set point, or do they expect it to be 24, or do they expect it to be less? And we're also removing the soiling factor, and this wasn't relevant to our model, but PHPP by default assumes that temporary shading is up when it sizes the cooling load, and that might be a consideration.
Just be good. On microphone.
Okay. And that might be a consideration when you're doing your sizing. So this is talking about how we adjusted the settings in PHPP. In your climate tab, we went through, we looked at weather in the 3 climates we analyzed and pulled out some data, and we thought, okay, we'll use this to do our analysis. Obviously, the temperatures that you size to, they're climate zone dependent, but they're also based on the expectations of your client. But we adjusted those in the climate tab. We increased Auckland by about 10 degrees to coincide with the hottest day that Auckland's had in the last 20 or so years. Wellington, we also increased. This was based on data from Greater Point, which reached 28.9 degrees on the hottest day. Interestingly, on exactly the same day, there was about 2 to 3 degrees of variation within Wellington between Greater Point and Calburn, which is also quite interesting. In Queenstown, we found that we should be using a temperature about 11 degrees higher. And this is based on Oliver Style's method, which is to look at your historic data to find max air temp, and then to use the corresponding dew point at the average relative humidity for that day as your inputs to your cooling load sizing model in PHPP. We found that the occupancy rates we used for certification tended to be a little bit lower. For the apartment, they were fine. For the 2 standalone buildings, we thought, actually, they're both 3 bedrooms, possibly better to use 6 people. Again, this is kind of a discussion between you and the client and how they will use their building. More importantly, I think, is the role of internal heat gains. So we found that we should be quadrupling the internal heat gains for the apartment we modeled. This is to do with relatively small living and kitchen areas. There's equipment giving off heat loads, giving off heat, which contributes to the cooling load. And for the standalone buildings, we also noted an increase, although it was slightly less pronounced, but still notable. And that's in the internal heat gains tab in PHPP. We left our cooling set points at 25 degrees, but important to check that. We removed the soiling shading factor from the shading tab, and we didn't need to change any of the temporary shading for the purposes of our models. We then basically took these adjusted PHPP inputs and translated them into the dynamic modeling space. I could talk all day about how we actually did that, but if you're interested, let's talk after. It's not as easy as it sounds. And ideally, we're looking for alignment between this adjusted PHPP and the single zone dynamic model, which is just one big room in Energy Plus. What we found was that the single zone dynamic model compared to the adjusted PHPP, we found that the adjusted PHPP was between 75% and 116% across all of the models that we did of this load. We also You can also note that the certification load is considerably smaller here. I'll talk more about why the 75%, well, why we think the 75% came up soon. We noticed that the adjusted PHPP and the single zone model aligned quite well in Auckland, but as we went further south, there seemed to be more of a misalignment. I suspect this is to do with the impact of solar radiation when the sun's slightly lower and the way this is considered in PHPP compared to dynamic energy models. And in the appendices of these slides, I've got a lovely graph of this. If people get the slides later, hopefully they can have a look at that. And an important point to note here is that when you have a building, there's a sort of a simultaneous load for the building as a whole. There's also loads for the different rooms in the building. These loads don't necessarily occur at the same time. And so actually, if you have a single zone model that agrees well with the dynamic single zone model, this is quite a good thing to use to size your outdoor units if you have a multi-split system. But yeah, going into the actual zonal model results, the expectation is that in the rooms we would have slightly higher cooling intensity, and the peaks would occur at different times of the day, depending on the orientation of glazing in the rooms. Looking at our standalone one building, as we're calling it, and this is just in Wellington, there's a few things to note here. So if I can use this laser, this adjusted PHPP line is quite a bit lower than the single zone energy plus model. This was actually the case where the adjusted one was only 75% of the single. And I'll talk about why that's the case very soon. We noticed that some of the rooms have considerably larger cooling intensities than other spaces, and on average, higher than what we're predicting in the adjusted PHPP file. If we actually look at this building as a whole, we find that on the eastern side, the peaks tend to be in the morning. The master bedroom with the largest cooling intensity has a particularly large window, which on our design day, it's getting a lot of solar gain, and that's why its cooling load intensity is so high. The bedrooms with some west-facing glazing had afternoon peaks, and actually quite late in the afternoon, in the evening, when the sun is really low. And the overall building had a peak at 6:50 p.m. in the single zone model. And something that we suspect from this, this is looking at the Wellington data, and which might explain why the adjusted PHP was so much less, is that PHPP maybe doesn't consider that low angle sun very well in the Wellington climate. And that's possibly related to how the weather was collected for PHPP for Wellington, and the impact of hills on the west in most parts of central Wellington. Looking at standalone 2, we see that the kitchen and living spaces have considerably higher cooling intensities than the other spaces. We see good alignment between the adjusted PHPP and the single zone model. The lines are almost on top of each other. This laser's not working. The lines are almost on top of each other. It's these two here. And the reason for the kitchen and dining and living having such much larger intensities is mostly to do with the glazing. And in particular, this kitchen and dining area has got corner with glazing on the north and the west, and it's just getting absolutely hammered in the mid-afternoon, and that's why it's so high. We also looked at an apartment, and this was a good test case to see if a building with relatively even glazing around it created more useful results. Again, we found that the peak was quite late in the afternoon, impacted by low angle sun. This is for the whole building. The individual peaks for the different rooms, as you'd expect, depended on the time of the day and the sun's position. In Wellington, we found again that this adjusted PHPP was lower than the single zone energy plus model. I again believe that's to do with the low angle radiation in the late afternoon. as it's the way that's considered in PHPP. We found that the western zones tended to have higher zonal cooling intensities and therefore higher cooling intensities relative to the adjusted PHPP. In Auckland, the western sides were also the most intense. The eastern sides seemed relatively a bit higher than they did in Wellington as well. And then going to Queenstown, we noticed that some of the north sides sort of bumped up a little bit as well. And this is probably because Queenstown is further south and the sun is lower to the north. Again, the solar gain impact. And again, sort of bringing us back to the intention of the cooling load number in PHPP, which is to be mostly used for well-shaded windows. Overall, the difference between our zonal cooling intensity and the overall cooling intensity in our adjusted PHPP varied widely. As you might expect, but on average, quite a bit higher, but even up to 3 times as high if we express it in a watts per square meter, as watts per square meter. And so, yeah, the general observations were more glazing means higher cooling load intensity, that if it was oriented to the west, the loads are generally higher. This is both in absolute terms, but also relative to the adjusted PHPP number and across all of the climates. But there was a lot of variability. We had a total of 97 data points with between all the simulations and all of the rooms that we did. Which is probably not enough to draw conclusions, but we still tried, and it wasn't really fruitful, unfortunately. Is what it is. So our conclusions are basically, if you're designing a building with a low window to wall ratio, very little east and west glazing, good summer shading to your north windows, and this is also important, no unusual peaks or client requirements. So if the use of the building is fairly consistent and constant, then PHPP might be useful. If it agrees with the high thermal mass, ability to absorb solar gain kind of building that's I can't remember his name. The PHPP, the original PHPP, the original passive house was designed to, then certification settings might be useful. If it's slightly lighter weight, or your cooling approach is to deal with peaks as they come, then the adjusted PHPP might be okay. But if you're designing a building that doesn't agree with all of those things, then it's probably better to use a zonal cooling approach when you're selecting your equipment. However, early on in the design, it's not always a good idea to go into that much detail. We'd suggest that an adjusted PHPP is useful for determining the load of the whole building if you adjust the settings. Obviously, as I've noted, if you're in Wellington and you think that the peak might be in the late afternoon for the whole building, then be cautious. And what you could do early on in the design is perhaps apply a multiplier to those perimeter zones, just as an initial sizing estimate early on in the design, so you're not spending tons of your client's money to get a zonal cooling estimate really early on. But a detailed design, yeah, we would recommend using zonal cooling loads. And yeah, that's that.